All right. This is our last section of the pieces and parts, which are going to give us in 4.6 those problems that have parts A through Z. The last thing we need to talk about before we hit those multi-step, all right, put everything you've ever known about graphing together on one problem, is horizontal asymptotes. Now, we've talked about vertical asymptotes before. Remember what the definition of vertical asymptotes were? If we had a vertical asymptote at x equals some number c, what did that mean happen to the graph? What happened to your y values as x approaches that vertical asymptote? Now my x's are approaching c. My y's are either going to positive infinity or negative infinity. That's the definition of a vertical asymptote. If there's a number c such that when x approaches c, your y's are going to infinity or negative infinity, then x equals c is a vertical asymptote. As I'm going to say, as x approaches c, y goes to plus or minus infinity. So, definition of a vertical asymptote. Today we're going to have definition of a horizontal asymptote. But before we do, I gave you a piece of paper. If you printed your notes this morning, then it had these 10 examples at the top. But if you didn't print your notes this morning, then I laid a piece of paper on your desk that has that 10 problems on it. Let's talk about those first. Vertical asymptote, your x is going to some constant, your y's are going to infinity or negative infinity. Horizontal asymptote, your x's are getting infinitely big or infinitely small. You're actually asking yourself, what is the end behavior of this function? What is it doing as x's go forever to the left or forever to the right? So let's look at these 10 examples. There's no steps in tonight's homework. There's just quickly hard and tell me the answer. And this is practice doing that. Remember what a fraction means? When I write 3 over infinity, that means 3 pi's divided by a bazillion people. If a bazillion people had to share 3 pies, about how much pie would each person get? Practically none. Pie is such a tiny, tiny piece that it's safe to say everybody's getting about no pie. Right. What about infinitely many pies divided among 3 people? How many pies does each person get? A lot of pies. Infinitely many pies, actually. Yeah, infinity divided by 3 is still pretty much infinity. What about whenever you see the infinity symbol, what if you just put in the word bazillion? What's 5 bazillion plus 2 divided by 5 bazillion plus 1? What is that roughly? Yeah. That if you're talking about 5 bazillion, it doesn't matter if you add 1 or add 2, it's pretty much still 5 bazillion. So that's 5 bazillion divided by 5 bazillion is about 1. But think about it, 5 bazillion and 2 divided by 5 bazillion and 1. Yeah. Does that make sense, Miss Lillian? Okay. Number 4, what about 5 bazillion and 2 divided by 3 bazillion and 1? Five bazillion and 2 divided by 3 bazillion and 1. It's darn close to 5/3. Again, because when you're dealing with 5 bazillion, adding 2 doesn't change it very much. And 3 bazillion plus 1 is still pretty much just 3 bazillion. So that's just about 5/3. Oh, I didn't hear that correctly, Lillian. You were right. I was hearing something else. I was confused. All right, number 5, e to the bazillion. What's 3 to the bazillion? 3 multiplied times itself a bazillion times. It's infinity. It's enormous. So any constant to the infinity, before I say that, nah, let me just not finish that. E to the infinity, yeah, is infinity. What about e to the negative infinity? Think of it as 1 over e to the infinity. And then, can you give me more? And can you give me more? That's about 1 pi divided by infinitely many people. Each person gets a chroma gain. Now, number 7, if you cancel the infinities, that'd be so very, very wrong. Sine infinity divided by infinity. Can you have do you have any way to think about that and come up with a number? No. One. No. You don't know what sine infinity is because you don't know, well, it oscillates. Sine doesn't approach something as x gets forever big or forever small. It just does the sine waves. What you can tell me is a range of values for sine. What sine is always between. No, you're telling me the parameters on one revolution of the unit circle. I'm talking about the value of sine. It's always between -1 and 1. It's going to oscillate forever, do the sine wave forever, but that's always going to be a number between 1 and 1, or -1 and 1. I'm trying to think of the best way to say it. This is all not mathematically accurate symbolism anyway. So I'm trying to think of a way to write that in a way that it would make sense. It's a number between -1 and 1. Does that work for notation, made up notation? What's any number between -1 and 1 divided by infinity? Okay. What about tangent of 1 over infinity? Well, just the 1 over infinity part is 0, and then what's tangent 0? At 0 radians, the y divided by the x would be what? Would be 0. All right. What about infinity? Infinity divided by the square root of infinity squared plus 1. That was so awesome. Tell me how you came up with that. Yeah, you could say kind of that the numerator and denominator are both first degree. That's so wrong to say that, but it's like 5 bazillion to the first divided by square root of 5 bazillion squared. Well, the square and the square root would undo each other, and this would just end up being bazillion over bazillion and 1. Bazillion over bazillion and 1 is just 1. And that's approximately infinity over infinity plus 1. And that's just 1. So this is how you're going to have to think about tonight's homework. And again, there's going to be no steps to write down. There are some algebraic things we could do, but I'm trying to get you to not have to do those algebraic things. I'm trying to get you to be able to squint hard enough to figure these out, and we'll have lots of practice at it. All right, what about number 10? Yes, because what can you tell me about the sign of that denominator? The square root of a negative square, the square root of anything using that symbol in the denominator means positive square root. So the denominator is approximately infinity plus 1. The numerator is negative infinity. And negative infinity divided by infinity plus 1 is darn close to negative 1. All right. So you see how we're going to think about it. All right, let's look at some of the notes, or probably all of the notes on this page. Limits at infinity. In chapter 2, when we discuss limits, the last section of chapter 2 was infinite limits. Let me make sure you understand the difference between infinite limits and limits at infinity. Infinite limits is where as x approaches some constant, your y's were either going to positive infinity or negative infinity. The answer was positive infinity or negative infinity. And remember, that's not saying the limit exists. That's saying the limit does not exist and saying why the limit doesn't exist. So if there was a problem that as x approaches c, my y's were getting infinitely big, we would write limit as x approaches c is infinity, but we were stating that the limit didn't exist, and we were telling specifically why the limit didn't exist. The difference here is it's not our y's that are going to positive or negative infinity, it's our x's that are going to positive and negative infinity. This function, f of x equals 3x squared over x squared plus 1. If we wanted the limit as x goes to infinity, in our heads, we could just put infinity symbols in place of both of those x's. What would you get if you had 3 bazillion squared over a bazillion squared plus 1? That's just darn close to 3. And you can see that by looking at the table. As our x's get close to, not x's get close to, as x's get infinitely small or infinitely big, my y's are getting darn close to 3. And you can also see that in the graph of this function. As a matter of fact, there's a horizontal asymptote at y equals 3. And as x gets infinitely small or as x gets infinitely big, your y's are approaching 3. That makes y equals 3, the horizontal asymptote. So the definition of horizontal asymptote, pretty much similar to the notation for the definition of the vertical asymptote. Remember, vertical asymptote is as x approaches c, y's are going to positive or negative infinity. The definition of the horizontal asymptote is as x's get infinitely small or as x's get infinitely big, there's some number that y is approaching, some number L. That limit exists and is L. Theorem 4.10 gave us some limits at infinity that we've already figured out. We figured out if we're looking at the limit as x gets infinitely big of some constant divided by x to a power, that's some like 3 pi's divided by infinitely many people. Each people get no pi, basically. And as x goes to negative infinity, that would be still a constant divided by negative 5 bazillion. That would still be 0. And the limit as x goes to negative infinity of e to the x. We had a problem where we had e to the negative infinity. We said e to the negative infinity is 1 over e to the infinity, and that's going to be about 0. That's what this one says. Or the limit as x goes to infinity of e to the negative x. Well, if your exponent was negative and then you put infinity into its place, you would have the same thing you had this first part. Both of those would be e to the negative infinity is 0. All right, one other thing, reminder from pre-calculus. When we're dealing with rational functions, remember the definition of a rational function is the quotient of two polynomials. So you got a polynomial in the numerator, a polynomial in the denominator. In pre-calculus, this was called the theorem on horizontal asymptotes, and you just memorized it, or you could make sense of it, but you didn't really know where it came from. That's because it comes from calculus, and we couldn't talk about it yet. But the theorem on horizontal asymptotes of rational functions. If the degree of the numerator is less than the degree of the denominator, let's say you have 5 bazillion over 5 bazillion squared, which is getting large faster, the numerator or denominator? 5 bazillion over 5 bazillion squared. The denominator is getting big faster. What is the value of a fraction if its denominator is getting big a lot faster than the numerator is getting big? And darn close to 0. If the degree of the numerator is less than the degree of the denominator, that means the numerator is getting big more slowly than the denominator, the whole fraction is going to be going to 0. And that matches what we said here. If your numerator is a constant, you divide it by infinity, you're going to get 0. Second part of that theorem is if the degree of the numerator is equal to the degree of the denominator, the limit, or the horizontal asymptote, is the ratio of leading coefficients. Like here, when we had 5 bazillion and 2 over 3 bazillion and 1, the degree of the numerator and denominator were the same. That limit, or that horizontal asymptote, would just be at 5/3. And then last, if the degree of the numerator is greater than the degree of the denominator, if the top of a fraction is getting big faster than the bottom, what's happening to your y's, or to the values of that fraction? Top, the national debt going to infinity divided by X number of people, it's going to infinity. If the numerator of a fraction is getting big faster than the denominator of a fraction, then there is no limit to that fraction, to the value of that fraction. All right. We should be able to whiz through these even problems. Now, this is not what you would see if you look in the book. And I did give you those, a copy of those, right? That's in the notes, or that is the notes for today. This is not what you would see if you looked at any examples in the book, but it's a skill that I want you to acquire for other reasons. So number 18, in my head, which is where I'm thinking that's 5 divided by negative infinity minus negative infinity divided by 3. X is going to negative infinity. Then here's the symbolic notation that's in my head. Now what's that first term? 5 divided by negative infinity. 5 divided by negative 10 billion is darn close to 0. If that numerator is fixed, dividing a fixed number by either positive or negative infinity is going to be 0. And what is infinity divided by 3? And what is 0 minus infinity? Yep. Oh, I didn't plug in negative infinity, did I? I plugged in a positive infinity. That's minus negative infinity, which will make that plus infinity. Oh, thank you. I don't know why I didn't plug in the negative infinity there. I'm glad you caught that. Number 20 is the limit as x goes to negative infinity of a rational function. That fraction is the quotient of two polynomials, which makes it a rational function. You can either think about your theorem on rational functions. If the degree of the numerator is the same as the degree of the denominator, then where's your vertical asymptote? Ratio of the coefficients, which would be what? 4. Or you can think 4 bazillion and 5 divided by 1 bazillion and 3 is about 4 bazillion. When we're talking about bazillion squared, adding 5 or adding 3 doesn't really make much difference. All right, number 22 is also a rational function. And the degree of the denominator is larger than the degree of the, no, they're the same. Huh, I don't know why they gave us 2 with the same degree, but what would that limit be as x goes to infinity? The ratio of the leading coefficients again, which is not 1. I heard somebody say 1. 1/2. Okay, right. 1/2. Are you going to like this homework? No, there's no work to show. Nothing for me to grade. All right. I think hard about this one, number 24. The limit as x goes to infinity of a constant divided by, well, let me say the constant is 6. 6 divided by 5 plus 2e to the negative 4x. Now, I may have to take several steps as I think about this, but somebody tell me what you're thinking. Because why? Oh, don't apply the theorem on rational asymptotes to expressions that aren't rational functions. Rational functions are the quotient of 2 polynomials, and that denominator is not a polynomial. So watch out for that. All right, somebody give me another thought. Tell me why. Tell me what you're thinking. Let me put in, you're thinking about this last term in the denominator. What we did in those first 10 examples I made up was when we had e to a negative, we put it in the denominator. No. E to the 4 infinity, or infinity is still infinity. What's e to the infinity? Infinity. And what is 2 divided by infinity? That's 6 over 5 plus 0, or just 6/5. Now, if there's anything that's not making sense, you need to stop me and say, I don't see how you thought about that one. Because I can try to explain it again. But if you just nod like everything's okay and we go on, you're going to get home with your question still bugging you. So far, so good? Okay. Number 26. The limit as x goes to negative infinity of square root of x squared plus, or x over square root of x squared plus 1. Talk to me. I would have negative infinity over square root of infinity squared plus 1. Yes, but the good thing about negative infinity is when you square it, you get a positive anyway. Negative infinity squared. So what will that denominator be? Just infinity. You square negative infinity, you get positive infinity. Adding 1's not really going to make a difference. Take the square root of that, and you're going to have negative infinity over positive infinity, which is negative 1. I just feel like I need to keep saying you won't see any of this notation in the book. I want you to be able to think about it and figure it out without having to do any algebraic manipulation. But in Calculus 2, that's going to mess with your head a little bit. I'm giving you a heads up on this. One of the things that bugs me most about Calculus 2 is 1 to the infinity is not 1. Yeah, that's when I almost changed to a PE major. Indeterminate form. What? I did say that. I did say that. Indeterminate form is when you have an expression that equals one thing some of the times and something else at other times. And that is indeterminate form. I don't want to go into Calc 2 right now, but it annoys the heck out of me that that notation seems to imply infinitely many ones multiplied together. It ought to be 1. It is sometimes. It's not. Yeah, that's, like I said, that's about when I changed my major to PE. Okay. Number 28. Limit as x goes to infinity of 5x squared plus 2 over square root of x squared plus 3. Tell me what you're thinking. That numerator is basically 5 infinity plus 2, which is just 5 infinity. Adding 2 is not going to make much difference, over square root of infinity squared plus 3. Well, that plus 3 is not going to make much difference. Square root of infinity squared is going to be what? Infinity, and 5 times infinity divided by infinity. I'm making lots of typos. Yeah, I don't know why I didn't have squared there. Well, it makes a difference though, because the degree of the numerator is higher than the degree of the denominator. The degree of the numerator is 2, the degree of the denominator is just 1. And so this does make a difference. What are you thinking? Does not exist. We can write it's infinity, but that is not saying the limit exists. That's telling why the limit does not exist. You have to be a little bit careful when you're using this notation and squinting hard to figure it out. It's tempting to say, well, infinity squared is infinity. Infinity times 5 is infinity. And this is just infinity over infinity, 1. You see how you would arrive at that logic? Yeah, but this infinity is getting big faster than that infinity. This infinity squared is bigger than that infinity to the first. I almost feel like not feel bad about putting that on a recording. I hope no one who's ever not in my class hears me say that, because it's not correct. Yeah. All right, number 30. What would you say the degree of the numerator is? Yeah, that's basically infinity squared, or actually negative infinity squared in the numerator and negative infinity cubed in the denominator. So what's that limit? The denominator's getting big faster than the numerator, so the whole thing's going to 0. All right, 32. Limit as x goes to negative infinity over 2x divided by x to the 6 minus 1, the quantity cubed, or to the 1/3, which is same as cube root. What's the degree of the numerator? So that's like 2 times negative infinity over, what's the degree of the denominator? Yeah, if you raise something to the 6th power and then to the 1/3 power, that's the same as squaring it. Technically, you cannot distribute 1/3 through a sum or difference, but you can say, by the time I've raised a bazillion to the 6th, subtracting 1 is not going to make much difference. So that's just negative infinity squared. This lady's not buying it yet. What do I think about that? Okay, this is a bazillion to the 6th. Minus 1 is really not going to make much difference. A bazillion to the 6th, the cube root of a bazillion to the 6th. All right. So what's that limit? The denominator is getting big faster than the numerator, so that whole thing is going to 0. All right, 34. Limit as x goes to infinity of cosine 1 over x. Before you tell me the answer, tell me a middle step. You're thinking 1 over infinity is 0. So that's cosine of 0. And cosine of 0 is what? 0 radians. The x is 1. All right. This last word, we need to take a deep breath. The limit as x goes to infinity of x minus cosine x divided by x. You can shout out an answer, but you're going to have to explain your answer. It's no steps. Your lips are forming the right word, baby. Yeah. Why? Something insignificant when the other term is going to infinity. And I certainly don't know. I can think of one way I could write that down. I don't know if it would be helpful or not, but you could split that fraction into 2 terms. You could say x over x is 1, and then cosine x over x would be the other term. Let me have that in parentheses. Yeah, a number between 1 and -1 divided by infinity is 0, and 1 minus 0 is 1. All right, number 38. the limit as x goes to infinity of 8 over 4 minus 10 to the negative x over 2. Sydney, did you say it? Who was that? Hold on, did somebody say the right answer? It was Neil. Okay, tell me why, Neil. Okay, let me write that down. 4 minus 10, oops, 1 over 10. 1 over 10 to the infinity. And 1 over 10 to the infinity is what? Yeah, which is 0. Good. Anytime I have something with a negative exponent, I put that term in the denominator, and it helps me see that it's the denominator getting infinitely big, and 1 over infinity is 0. All right, number 4. Limit as x goes to infinity of 5/2 plus natural log of x squared plus 1 over x squared. Tell me what you think. Yeah, because infinity squared, a bazillion plus 1 divided by a bazillion is pretty much 1. You know, that adding 1 doesn't make much difference. You could just look at that part and say the theorem on horizontal asymptote says if the numerator and denominator are getting big at the same rate, then the limit is, as x goes to infinity, is the ratio of the leading coefficients. Yeah, so that's 5/2 plus natural log of 1. And natural log of 1 is 0. So that's just 5/2. Woo, one more. Don't worry. The limit as x goes to infinity of arcsecant u plus 1. Limit as u goes to infinity. Well, I know that infinity plus 1 is still pretty much infinity. So really this is just arcsecant infinity. How do I figure out what the heck that is? Talk to me about arcsecant. Angle whose secant is infinitely big. How can I change that to arc cosine? Is it 1 over arc cosine? Arc cosine of, right. The angle whose secant is infinity, its cosine is 1 over infinity. Not 1 over arc cosine, it's 1 over infinity. 1 divided by infinity is 1. Oh, that's arc cosine of 1, or 0. Arc cosine of 0. And that's the angle whose cosine is 0. Angle whose x is 0. Your x is 0 at the whole pies? Half pies. And remember, arc cosine always gives you an angle between 0 and pi. So what's the angle between 0 and pi where cosine is 0? Remember that tangent, secant, and cosecant have vertical asymptotes. So the inverse tangent, inverse cosecant, and inverse secant have horizontal asymptotes. It's just those vertical asymptotes turned on their sides. And as x is getting infinitely big, arc secant's horizontal asymptote is at pi over 2. All right. Any questions? Have we ever in the history of calculus finished 6 minutes early?
More than 6 minutes.
Wow. Oh, darn. It's 11 minutes early. That means you can ask me questions about life. Or you could go get breakfast. See ya. Y'all have a good day.